think we are going more to materials spec and about reusing resources. The title of the talk is From SOC stack metal scraps into space-grade steels, a tale of sustainability. Please, the stage is yours.
Let's take a journey back to around 55 years ago to this truly momentous milestone in human history, the moon landing. However, I'm not going to talk about the moon landing itself, but rather this remarkable device that was brought along by the Apollo 11 mission. This is one of the 3 fuel cell stacks that provided electricity to the spacecraft and supplied clean drinking water to the crew. Remarkably, this was also the first successful commercial use of hydrogen in fuel cells, marking a giant leap not only in space exploration but also in the advancement of electrolysis technologies. Fast forward to the modern times, and we see this little guy in numerous applications. For instance, in transportation, and this time with terrestrial vehicles, where hydrogen fuel cells serve as an alternative to electric batteries. Hydrogen is also primarily used as an industrial feedstock in many chemical processes, notably in ammonia production, which is essential for manufacturing fertilizers. Steel sectors are also gradually replacing coal with hydrogen as the sole reductant for iron and steel making. Today, global hydrogen production stands at an impressive 95 million metric tons per year. However, today's hydrogen is dirty because it is produced from steam methane reforming process, which heavily relies on fossil fuel and releases unabated carbon dioxide into the atmosphere. Therefore, we need to decarbonize this hydrogen production in order to achieve our climate goals. Decarbonization scenarios are calling for a 5-fold increase in this hydrogen demand by 2050 and a paradigm shift from this dirty gray hydrogen to cleaner hydrogen alternatives, the bulk of which must come from the so-called green hydrogen. This is produced via water electrolysis and using renewable energy sources, so it's virtually carbon dioxide free. The International Energy Agency predicts 3,300 gigawatts of global electrolysis capacity target to meet this green hydrogen demand. And that's about 3,000 times jump from the 1 gigawatt capacity we had in 2022. As you can see, this target is quite ambitious and requires global, collective, and accelerated effort. So far, 22 countries have announced their green hydrogen pledges, including Germany, that aims to produce 10 gigawatts of electrolysis capacity by 2030 through the flagship project H2Giga. As the name suggests, H2Giga aims to industrialize this production of fuel and electrolysis cells in the country, thus making green hydrogen more affordable and easily accessible. With this industrialization, however, we also need to anticipate this massive wave of future technological waste. And to address this, we have this RENARA project, which has also been launched to develop recycling pathways tailored to prospective electrolysis technologies, such as this Ulish solid oxide cell stacks, as illustrated in this slide. In my research, we focused on recycling this interconnect assembly, which is one of the main components of this SOC stack and constituted of these nickel meshes and copper alloy-based interconnector. Recycling these parts is crucial because cost analysis for large-scale Ulish stack production has revealed that the materials, in particular these interconnects, take the highest percentage in the manufacturing cost. Furthermore, interconnects also dominate that stack in terms of net materials demands, taking 72% of the total stack weight and containing critical resources in the form of iron and chromium from the copper, nickel from the mesh, and cobalt, manganese, and lanthanum from the coating layers. The good thing about these parts is that they are steel-based, and steel is in principle infinitely recyclable. The question, however, is what type of alloy we can produce if we melt down the whole thing? To answer this question, we did thorough characterization that involves microstructural analysis to determine what layers are adhering onto our copper substrate. We also did many thermodynamic and experimental melting trials to determine what elements tend to oxidize more easily in our sample. And from here, we found out that cobalt is inert and wants to stay in the bulk alloy. This finding is significant, so please keep it in mind for later. So through our characterization, we concluded that the sample is primarily composed of iron, chromium, and nickel, with less than 3% of trace elements such as cobalt and manganese. This composition closely resembles an AISI 304 steel, which is a commercial-grade austenitic stainless steel and belongs to the most common and versatile type of steel families. Due to its properties like exceptional heat and corrosion resistance, we can find this steel in many applications, including chemical storage, heat exchanger, and even the manufacturing of your common kitchen utensil and cooking ware. Interestingly, this type of steel that we use for cooking and eating is the same type that is used for manufacturing of Elon Musk's SpaceX starships, which are being developed for Mars and Moon exploration. So, the big question is, how can we cook this interconnect scrap and turn it into space-worthy steels? Of course, to answer this question, we have to refer to our steel-making cookbook and start from there. The good thing is that steel has been extensively studied, and the art of steelmaking has a long and well-established history that involves smelting, refinement, and heat treatment operations. So to evaluate the success of this scrap-based steelmaking route, we have to see if we can produce a 304 steel at the end. And we can do this by examining these three interconnected pillars in this triangle, the microstructural, mechanical, and compositional properties of the resulting alloy, and then compare that with the target 304 steel. The first property we evaluate is the microstructure. So if we melt down this entire interconnect assembly, do we produce a fully austenitic steel? To answer this question, we refer to the equilibrium phase diagram of the sample and see at which temperature ranges the austenite phase is stable. And according to this, austenite is stable at temperatures above 900 degrees Celsius. Furthermore, it is also thermodynamically possible to observe austenite at room temperature, but this time ferrite also forms alongside this phase. So we melted the sample, held it at its austenitization temperature, and then water quenched it to freeze the microstructure. By doing so, two things can happen. First is that the microstructure would follow this equilibrium phase diagram, and we would observe a predominant austenite microstructure with small amount of ferrite phases. Second thing that could happen is that austenite would transform to martensite via non-equilibrium diffusion-less transformation. And this particularly happens when the alloy is being cooled below its MS, or the martensite start temperature. So results have shown that the resulting microstructure is predominantly martensitic, as you can see with this red face map here. And therefore, austenite wasn't prevailing at ambient temperatures. One thing we have forgotten, in the production of the austenitic steels like 304 steel, particular attention has to be given to this nickel equivalent value to ensure that austenite remains retained at room temperature. And this is calculated based on the weight fractions of certain austenite stabilizing alloying elements multiplied by certain weight factors. For the 304 steel, its value is within the range of 8 to 14. For the base metal, it's at 8.4, which is at the lower end, and this might be the reason why austenite was metastable. Hence, we did refinement experiments, in particular alloying, such that we increased the manganese to around 2%, nickel to around 9%, and nickel and manganese to around 9 and 2% respectively, all with the intention of partially increasing these nickel equivalent values. So results have shown that the addition of manganese did not help stabilize the austenite, as you can still see with this red face map here. But the addition of nickel, and both nickel and manganese have yielded blue austenitic phase maps with small amounts of these yellow ferrite phases, which is about 4%. So at least with these two refined alloys, we can see that we are achieving an austenitic microstructure even with the presence of these ferrite phases, because standard 300 grades may contain up to 5% ferrite. So this might be good enough for us. Next question, where is MS, or the martensite start temperature? We can determine this via the technique called high temperature XRD, wherein we record the temperatures at which the martensite BCC peaks start to form during cooling. And according to this graph, the MS ranges are all slightly above room temperature. But the intensity of these martensite BCC peaks forming as a function of temperature varied significantly across these investigated alloys. This intensity is correlated to the amount of martensite forming as a function of temperature. Notably, for the 9Ni2Mn, we see slow martensite transformation kinetics, and therefore austenite remains retained and predominant at room temperature. So we can make a big check here in terms of achieving the microstructural requirement for the target 304 steel. Next is the phase area fractions. We want to validate the phase area fractions that were determined on a really small region within a larger polished surface. And we can do this via the technique called microindentation testing, wherein we determine the Vickers hardness values on random points within the larger region. These Vickers hardness values are correlated to the phase area fractions such that a microstructure with coexisting martensite would be harder than the one with austenite. Results have shown that the base metal, as you can see here, has the highest martensite fraction. And here, it has the highest hardness value attributed to this martensite fraction, followed by the 2Mn alloy. Interestingly, for the 9Ni, although we saw beforehand that it might be predominantly austenitic here, we see a high standard deviation, which might indicate that the phase is highly inhomogeneous. Finally, for this 9Ni2Mn, we see low hardness value and low standard deviation, indicating that the microstructure was homogeneously austenitic. Furthermore, its Vickers hardness values are falling within the expected range for a solution annealed 304 steel, so we can make a big check here in terms of achieving the hardness property of this 304 steel. So far, so good. Now we only need to see the composition. So we compared the composition of the best refined alloy with that of the target 304 steel, and we found out here, however, that cobalt is outside the tolerance limit. And this might be due to the earlier findings that cobalt is inert and wants to contaminate the bulk alloy even at oxidizing atmospheres. Hence, we have to modify a little bit our recycling route in order to remove cobalt. The good thing about our sample is that cobalt is concentrated on the coating layers, specifically on this MCF coating here. Hence, we can add some interconnect decoating steps in order to remove and recover cobalt and other coating elements that would otherwise contaminate our product steel. These decoating steps are constituted of acid pickling and precipitation. Due to time constraints, I have to focus only on the results from acid pickling tests. As the name suggests, acid pickling involves submerging the entire sample in an acidic media, like this one. And the coating elements are presumed to go to the leachate, and the pickled specimen is sent for steel making. Taking a closer look on the surface of the sample during the pickling process, we presume that the coating elements get dissolved by the acid, and this is evident from this gradual removal of the coating layers as we increase the pickling duration. So we would try to obtain the optimum cobalt pickling efficiency by varying different parameters like time, temperature, solid to liquid ratio, and so on. The problem of this setup, however, is that the Crawford alloy also gets dissolved by the acid, forming pores, as evident in this image here. So how can we remove these coating elements with minimal acid dissolution of the Crawford alloy? To solve this, we added the so-called metal inhibitors in our acid pickling solution. The mechanism of these inhibitors are quite complex to discuss, but to put it simply, these are organic compounds that have a functional group that absorb or react on the surface of the Crawford alloy, forming a thin protective film that protects it against the acid. Meanwhile, this oxide coating, due to its different electrochemical property, continues to get exposed and dissolved by the acid. So we tried 3 different metal inhibitors and assessed their alloy inhibition efficiency. In this graph, you see these bubbles, right? The smaller the bubble size and the higher it is located in the y-axis, the better it is in minimizing the dissolution of the Crawford alloy. And based on these results, these blue additives called the hexamethyl enantetramine are the best one, yielding the best inhibition efficiency for the alloy and effectively minimize the formation of the pores, as shown in this image here. Finally, pickling using this additive and under the best pickling conditions have yielded a cobalt pickling efficiency of 98% and a final cobalt content of 0.02 weight%. Now we are confident to say that we achieved the compositional limits of the target 304 steel. In conclusion, we demonstrated that we achieved the microstructural hardness and compositional properties of the 304 steel via recycling of the Jülich SOC stack interconnect assembly. 50 years ago, fuel cells were used to power the very first space mission. Today, they are now used to power our society. In 50 years' time, we can envision sending this very same technology back into space in the form of steel from recycled interconnects. Indeed, sustainability and innovation can go hand in hand in propelling us towards new era of exploration. Thank you for your attention. As to my plans after my PhD, to be honest, I don't have a concrete plan yet, but I'm a metallurgist at heart, and I plan to, or I intend at least, to stay in research, specifically on green steel research. This is steel made with green hydrogen or green electricity, and it's quite a hot topic right now in Europe due to its role in decarbonization, with many projects being funded left and right in both research institutions like here and industry. So this is where I want to work in the future. But now, I still need to finish and defend my thesis. Thank you for your attention. If you have any questions, I'm ready to answer them.
Yeah, thank you for the presentation. First question is by Sebastian.
My question is, if we're talking about industry scale recycling of SOCs, I mean, all those steps seem pretty complex to me, at least. What's your opinion on scaling up the process?
That's a really good question. So we have a consortium of different institutions, and we also have partners from the industry. So some of us, or at least some of the research institutions, are tasked to do the fundamental research, because this research has never been done before, specifically the recycling of SOC. So we are doing this in Forschungszentrum Jülich. I also have a colleague that is doing the self-recycling, and our plan is to scale it up. So we have partners, specifically from RWTH, Aachen University, who are assisting us to scale up this whole recycling route from the coating to the steel making. We have done the whole recycling route like few weeks back, and now we are analyzing the results. But that's the goal. Yeah, that's the goal.
Gunnar?
Yeah, so I wonder, so you described your process taking these fuel cells and the interconnectors into steel. How different would that be, or could you use a very similar process to slightly different or other devices or other things that need to be recycled, not just that thing, but or is that really very specifically targeted to exactly these types of interconnectors on fuel cells?
Yeah, thank you very much for your question. Yes, that's true. The goal of this recycling route, to make it marketable or attractive to the industries, is to make it readily adaptable to accept also scraps from other sources. That's why I started with a very basic scrap-based steelmaking route. But then again, I had to check the composition of the product steel, if it's still within the limits. And since it wasn't, I had to add some interconnect or like a pretreatment steps for that. But the goal of this recycling route is to make it adaptable as well to accept scraps from other steel sources, secondary steel sources. Yeah.
Okay, then first the question in the middle.
Yes, thank you for the presentation. I just wondered, if you remove the cobalt, does this change the mechanical properties of the material?
Yeah, that's a very good question. Thank you very much. Cobalt is, to be honest, is a weak austenite stabilizer. So it also has an effect on the microstructure of the steel. But then again, the product or the target 304 steel, the cobalt present there is a trace element. It's not an alloying element. It's a trace element that is unavoidable during steel making, but we have to remove it because it has certain negative impact on the properties of the target 304 steel. So, but since it's a trace element, removing it entirely wouldn't significantly impact the phase balance of the 304 steel. Yeah.
Thank you. I have a follow-up question,
Okay.
if it's okay. So for the removed cobalt then, is it possible to use it for other application?
That's a very good question. Thank you very much. I did not show you the whole recycling route, but there is a step after acid pickling, and that is precipitation. The goal of precipitation is to recover cobalt from the leachate, from this solution, to produce concentrated powders. We are actually successful in producing concentrated cobalt concentrated powders up to 10%. And the outlook here is to send this to recycling facilities that can further increase the concentration of cobalt through probably electrowinning processes. But we want to recover cobalt because, again, this is a technology critical element that needs to be recovered rather than lose via alloy dilution, for example.
Thanks. This sounds pretty fascinating.
Okay.
Okay, then let's close this talk, and thank you again.
Thank you very much.
And our next speaker